Now that we have talked about random variables and we talked about expected value and the variance, one important question that we always ask when we look at the values of a random variable and expectation is, how large can a random variable be? Okay? In other words, we can ask, how far from the mean can values that random variable take? So if I say, for example, that the expected value of a random variable, suppose I say the expected value of a random variable is 2. One question to ask is, how likely is it that x is million, for example, okay? So if the average is 2, how likely it is, or what's the probability that x can take the value million, okay? Why is that important? Because when we compute the average, one of the interesting questions for us is that how representative is the average? Again, as I said before, if I say the average grade in the course is 70, now how representative is 70? It's one thing to say that all the students are making 70, in which case the average is very representative. It's another thing to say the grades are between 65 and 75, in which case the average is still a good indication of where the grades are. But it's a different thing to say the average is 70, but some students made 5 out of 100 on the exam, and some students made 100 on the exam. So here, if I report the average, the question is, how far can the values be distributed away from the mean? Okay, so if we look at a distribution, for example, like this, a distribution of the probability distribution of a random variable, and the mean is usually somewhere here. Okay, the mean is usually somewhere here. This would be the value of the mean. Okay, so this is the expectation. But if you look at this distribution here, there are values that could be here, and this is what we call the tails of the distribution. Okay, and this is a word that's used often when we are talking about distribution. So you hear about distributions that have a very long tail or a very fat tail and so on. What is meant is that these are the extreme points of the distribution. So if you look at the tails of this distribution, then you can start thinking of different scenarios where the mean is more meaningful in some than in others. So if we go back here and I draw two distributions, for example. So if I draw this distribution here, and I look at the mean, and here's another distribution like this, and I look at the mean here. Okay, so this is the mean, and suppose this is for a different one. If you look at it on the right here, what we are seeing in this case here, that the points are not distributed very far from the mean. Okay, you cannot go too far. The tails are not so far from the mean, whereas here the tails can be very far from the mean. And we are interested in knowing how far can we be from the mean, or putting some bounds. Okay, so putting some bounds. In other words, we are saying the probability that you are this far from the mean is at most, let's say, 0.1. This is the question we would like to answer. And this question falls within a topic that we call tail bounds. Okay, tail bounds. So we want to put bounds on the tails of a distribution. Okay, and for example, one of the important uses here, we have already seen how we use the expected value to analyze the running time of the average case running time of linear search. So if we say the average case running time of linear search is O of n, well, O of n is the average, but is it possible that for some inputs, for example, a linear search will take n squared and so on? So the question we are interested is that what is the probability that x takes n squared, given, for example, that e of x is n, let's say, okay? So how far can we be, and what's the probability? In these kind of probabilistic settings, usually the random variable can be very, very far from the mean, but the distribution starts decaying. The probability of that happening starts decaying. Okay, and one of the very first bounds that we use, or one of the loosest actually bounds that we use on for this case, is known as Markov's inequality. Markov's inequality. Okay, and Markov's inequality is very simple, and we can derive it directly here. So let's look at the expectation of x. Remember that the formula for this is that it's the sum over all x's, and this the value that the random variable takes times the probability. Now, if you look at it, this x's here, the little x, let's take any arbitrary number that we are interested in. So I'm interested in saying and asking, for example, what's the probability that x can be larger than some value a. I'm interested in this. What's the probability that x is greater than or equal to a for some a? Okay, so suppose we are talking about grades. I'm interested in asking what's the probability that x, which is the random variable corresponding to grades, is greater than or equal to 80. Okay, and if given that I'm interested in a, now I can split this sum into two summations here. I can look at all the x's that are smaller than a, p of x, and I can look at all the x's that are greater than or equal to a, p of x. Notice that I haven't really done anything fancy here. The first line here says sum over all x's. If we sum over all x's, I divide it into two cases. I'm summing over all the x's that are smaller than a, and all the x's that are greater than or equal to a. Okay? If you do it like this, we know that this is greater than or equal to x smaller than or equal to a, 0 times p of x. Okay? Because x is greater than 0 here, and the sum over a p of x. Okay, so where did this come from? Since for the second part here, let's look at it. For the second part, we know that x is greater than or equal to a. So this summation here, if you replace x by a, this becomes, this one is larger than or equal to this one here. Okay, and we are talking here about random variables. I should have said this. They're talking about random variables that take non-negative values. Okay, so I'm assuming here that x is greater than or equal to 0. And this is what allowed me to say that this here now is greater than or equal to this. Okay, but now if you look at it like this, this is 0 here. So this equals the sum of a, p of x, for all x greater than or equal to a. And this, I can take the a outside here, and I can say this is a, the sum over all x greater than or equal to a of p of x. But this here, what we write here, this term, I can write it as this equals a p of x greater than or equal to a. So if you look at this now, what we got is, if you look at what the top line and the bottom line here, what we got is really this. E of x is greater than or equal to a, p of x greater than or equal to a. Okay? In other words, I can say that p of x greater than or equal to a is smaller than or equal divided by a. And this is Markov's inequality. So Markov's inequality relates the probability of how big the x can be to its expected value. Okay, so if you think about it here, for example, and if we talk about, let's say again, we are talking about grades in a course, and someone says, well, the average grade in the course was 55, and someone asked, but what's the probability that some student made a grade higher than or equal to 90? Markov's inequality tells us that the probability that someone made a grade higher than or equal to 90 is smaller than or equal to 55 divided by 90, okay? So this here, if you look at 55 divided by 90, it's not very far from half actually. So this is not a negligible, it's not a negligible value here, okay? But the issue again is that, notice here, I'm not saying it equals 55 divided by 90. I'm saying it's less than or equal. This is why we call it a bound. We are saying that the probability that some grade is higher than or equal to 90 is bounded from above by 55 divided by 90. It's not higher than that, okay? So this is Markov's inequality that, again, if I highlight it here once again, it's this region here, it's this formula in the circle here, that the probability that x can take on a large value, which is basically we are saying x greater than or equal to a, is smaller than or equal to e of x, or the expected value of x, divided by a. Now, one big issue with this is, hopefully you will immediately notice, is that this bound, Markov's inequality, makes absolutely no use of the variance. And we have already talked about that this would be an issue, because if I give you two distributions, again, one like this, like, I'm going to exaggerate it a little bit, and another distribution is like this, the probability of having a large value under the left distribution is higher than the probability of having a large value under the right distribution, because the left distribution is very diffuse. It's very diffuse here. The values the tails are very, very wide apart, and the values can be very large. Whereas for the distribution on the right, that cannot happen. So Markov's inequality doesn't understand this. Markov's inequality is not going to make any distinction between these two cases. So if the mean in the left distribution is 3 and the mean in the right distribution is 3, well, Markov's inequality, all it understands is 3 divided by a. For both of them, it's going to be 3 divided by a. So the probability of x greater than or equal to a is less than or equal to 3 divided by a under both distributions. But this doesn't make sense. I mean, it's correct, but it's way too loose, especially for the right-hand side distribution here. So we are interested in coming up with a bound that allows us to take the variance into account, and this takes us from Markov's inequality to Chebyshev's inequality, okay, or Chebyshev's bound, Chebyshev's inequality. Okay, so this also puts a bound, slightly different bound here, but also it makes use of the variance of the random variable. So if we have a random variable x, and if you take any real number that's positive, this is r is a real number, we are interested in bounding how far can the value be from the mean. Okay, so what's the probability that the random variable takes a value that is greater than or equal to a away from the expected value? So x minus e of x, here we are saying, again, this is the difference between the value and the mean value. How far is x from the mean value? We want to actually look at a bound for this difference from, or distance from, the mean value. What's the probability that this can be very large, or larger than or equal to a? And Chebyshev's inequality bounds this by the variance of x divided by a squared. So now this is much tighter than Markov's inequality for two reasons. First of all, it's actually now normalized by a squared, not just by a. And the second thing is this makes use of the variance of the random variable and not just of the expected value. Now, where does this come from, or how do we derive this? It's actually, the derivation is very simple, because if you look at the probability of x minus the expected value of x greater than or equal to a, this is the same probability as p of x minus e of x squared greater than or equal to a squared. Okay, actually I don't know why I said r here. This should be a, sorry. I'm using A, so it's A here. So the probability of the absolute value of x minus ex greater than or equal to A is the same as the probability of x minus e of x squared greater than or equal to A squared. Okay, but now we can apply Markov's inequality, where we are now talking about, sorry, let me use a different color here. So if you take this now, if we take this as a random variable, let's call it y, for example. So now I see the form of Markov's inequality, where we have p, what's the probability of y greater than or equal to A squared, right? This is, by Markov's inequality, is smaller than or equal to E of y divided by A squared. This is from Markov's inequality, right? So if we go to this and we look at y, then the probability of x minus e of x squared greater than or equal to A squared, this is smaller than or equal to e of x minus e of x squared divided by A squared. But if you look at this, what's on the numerator here? This is v of x, the variance. Okay, so this is, if you look at the left hand side and the right hand side, this and this is what Chebyshev's inequality tells us. Okay, the probability of x minus e of x squared greater than or equal to x squared to A squared is smaller than or equal to v of x divided by A squared. And again, since this is equal to the probability with the absolute value, we have the same result, right? So again, this is equal to the probability of x okay, so this equals this now. Okay, here we can put less than or equal. So this is Chebyshev's inequality, and again, it's just it follows up from Markov's inequality when we look at x minus ex squared, and we take that in terms of the, once we take expectation of that, then we have the variance. Okay, now if we look at this, it's very important to put them all both side by side. So Markov's inequality is the probability of x greater than or equal to A is less than or equal to e of x greater than A squared, than A divided by A, not A squared here. Now if I take a specific value here, so if I say, let's take P of x greater than or equal to A. So if I replace A by A times E of x, so some constant times the mean, then this is smaller than or equal to E of x divided by A E of x. So this becomes the probability that x is greater than or equal to A E of x smaller than or equal to 1 over A. Okay, so this is a corollary of Markov's inequality, that the probability that x is larger than A times the mean is less than or equal to A. Okay, now if we look at Chebyshev's inequality, it tells us that the probability that x is farther from the mean by A, and let me actually now put a standard deviation here, I will get less than 1 over k squared, okay, or A squared, sorry. Let's actually erase this here. So I wrote it in two different ways now. Let's take this here. So if I look at this from Markov's inequality, I'm saying that the probability that x is more than A times, is farther than A times the mean is bounded by 1 over A. if I look at Chebyshev's inequality and I use that special constant there, which is a sigma, where sigma is the standard deviation, then if we look at this one here, that this bound is less than, or this bound is 1 over a squared. What does this basically say? What am I saying here? Is that Markov's inequality, it's putting a bound that decays linearly with a. Okay, so Markov's inequality says that the probability of being farther than the mean by a times decays linearly. So if you double a, then the bound actually decreases by half. Chebyshev's inequality, it says that the bound, it puts a tighter bound here because the bound decays quadratically. So if you double a, then you're going to divide that bound. You're going to get a bound that's smaller 4 times than the original one here, okay? But if you look at them, it's very important to notice there's difference here. One of them, again, because of I cannot change these inequalities, all I'm doing here is just using, instead of a, I'm using different constant. So with Markov's inequality, all I'm saying is that the probability of x greater than or equal to a times e. What I'm saying is that x greater than a times the mean. For Chebyshev's inequality, I'm saying the probability that x is away from the mean by a standard deviations. Okay, so if we want to say this in English, what is this here? P of x minus e of x greater than a this. If we write this, what we are saying in English is this is the probability that x is at least a standard deviations away from the mean. Okay, so when we report averages, usually we also report the standard deviation. Okay, and we are interested in how many points fall 1 standard deviation from a mean, how many points fall 2 standard deviations from the mean, and so on. So this here, what I wrote, is the probability that x is at least a standard deviations away from the mean is bounded by 1 over a squared. So the farther it is from the mean, the farther that distance from the mean, the lower the probability that can happen. So this is saying that x cannot be arbitrarily far from the mean. Okay, so if you take larger and larger x's, the probability that this value will be attained by this random variable is going to be bound by 1 over a squared. Okay, and one of the nice uses of Chebyshev's inequality is actually to put bounds on a number of iterations, or the bounds on errors of algorithms. While I'm not going to be showing it in this video here, if you look at the slides on discrete probability that are provided for the course, at the very end you will see an example of what I call Monte Carlo algorithm for estimating pi. Okay, so what is the issue there is that suppose I want to write a computer program that allows me to estimate the value of pi. Okay, so pi, of course, has an infinite representation, so it has an infinite number of digits. But I want to get someone ask me, can you enumerate for me the first 10 digits after the decimal point? I don't remember that, but I have an access to a computer and I can write a program, for example. So how do we estimate the value of pi using what we call simulations? Well, one simple way to do it is, imagine that you have a square with the sides of the square being 1, each side is 1, and you have a circle, and now I'm terrible at drawing circles here, so suppose I have a circle that touches all the sides of this square. So if you look at this, the radius of this is 1/2. Okay, the radius of this circle is 1/2. Now, if you look at what's the area of a cycle, it's pi. If we look at the area of the circle, it's pi r squared. Okay, so it's really pi times 1/4. And the area of the square is 1. So now, here's how you write a computer program. So you, for I equal 1 to n, you repeat the following process n times. You throw a darts, think about this as a board where you throw darts at the square. And what you do is that you throw darts here. So I'm going to throw darts, and I'm going to color the darts that fall inside the circle with black. So I'm throwing darts, and some of them fall inside the circle, and some of them are going to fall outside the circle but in the square. And this is the only region where they can fall, either inside the circle or outside the circle but inside the square. So now if you look at this and I want to estimate pi, what do we do? Take the number, if you take the number of red dots, or sorry, the number of black dots here, so the ones that are inside the circle, and you divide it by the number of the total number of dots that you throw, which is basically the number of black dots plus number of red dots. What do you expect this to be? So how many darts you think are going to fall inside the circle? It's going to be proportional to the ratio of the area of the circle to the area of the square. So this ratio here should be equal to or proportional to 1/4 pi divided by 1, which is 1/4 pi. So if you took, so what I'm getting from this, if I throw the dart n times, and if I throw the dart m times, and then n times total, out of these n times, m times fell inside the circle. Okay, m times fell inside the circle. Then m divided by n is proportional to 1/4 times pi. So pi can be estimated as 4 times m divided by n. So a simple algorithm to estimate pi is the following. Throw darts at this square, count the number of darts that fall inside the circle, divide that number by the total number of darts you threw, multiply by 4, you will get this estimate of pi. Again, if you look at the slides for the discrete probability part, you will find actually the actual pseudocode of this algorithm. But where do tail bounds come here? The tail bounds come here in answering the question, how many times do I need to throw the dart to get a good estimate of pi? For example, just think about it. If you throw the dart once, of course you're going to get a terrible estimate of pi. So if you throw the dart once and you get one dart inside the circle, you're going to estimate pi to be 4. It's 1 divided by 1 times 4. It's 4. If you throw 2 dots, so if we look at it, for example, so if I talk about number of throws of the number of darts, and suppose I look at number of darts in the circle. So if I throw the dart once, suppose there's 1 inside the circle, then my estimate of pi that I can denote by pi hat, remember it is the number of darts inside the circle divided by total number of darts times 4. So it's 1 divided by 1 times 4, it's going to be 4. If you throw 1 dart and you get 0 here, it's going to be, estimate of pi is 0. So terrible estimates of pi. But suppose you throw 20 darts and inside the circle you get, let's say, 15. Okay, so now it is 15 divided by 20 times 4, which will be about 3, right? So 15 divided by 20 is 3/4, times 4 is 4. So now this is getting closer to this, and suppose you throw it 100 times, and if you throw it 100 times, for example, suppose you get it inside the circle, let's say 80 times. So now it is 80 divided by 100 times 4, and you get the value. So the question is that, of course, the more you throw the darts, it's more time for the algorithm because it's just doing more and more iterations of these calculations. The question, at what point here, how many should you throw the dart so that you get an estimate that's close to 3.14 up to a certain digit. We can use Chebyshev's inequality to help us estimate that number. Okay, so depending on the error that you are allowing to tolerate. So for example, if you say, I want pi to be within two, to be exactly the correct digits up to the 5 digits after decimal point, then Chebyshev's inequality gives you a bound on how many times you need to throw this dart. Okay, I am not gonna go through this here because on the slides I have the full example worked out in detail there, and you should be able to follow it and see the use of Chebyshev's inequality for that as well. Okay, so just to summarize this part, again, we saw expected value of a random variable, we saw the variance of a random variable. The tail bounds are basically bounds that we have on how large a value a random variable can take. Because the mean tells us what's the average value that the random variable can take. But this average value, you can have values that are much, much farther from it. And these tail bounds tell us something about what's the probability of being too far from the mean. Okay? And these are very useful. And when we analyze the error rate, for example, on randomized algorithms, or again in this kind of simulation-based algorithm where I want to estimate pi, these bounds allow me to mathematically get an estimate of how many times I need to throw the dart. Because remember, when I'm trying to estimate pi, I don't know the exact value of pi, so I cannot look at the value and say, oh, I know it's correct up to the fourth digit or not. Mathematically, I can say that using Chebyshev's inequality, I can say how good is a certain number of throws of the dart would be when I'm trying to estimate the value of pi.